All right, so today we're going to talk about what a midpoint is, how to use the idea of a midpoint and locate the midpoint. And we're going to talk a little bit about finding the length of a segment or the distance between two endpoints, which, good news for us, is going to be the exact same thing. So by the time we're done here, you should be able to find the length of a segment in a coordinate plane. You should be able to not name, measure, and classify angles. This shouldn't be here. But anyway, be able to locate a midpoint and find the length of a segment in a coordinate plane. Okay? So, first and foremost, a midpoint. What is a midpoint? Well, a midpoint is a point on the segment that divides the segment into two congruent segments, right? So it sits in the middle. Midpoint, middle point, right? So it'll create two congruent segments. It'll break one segment up into two congruent segments. We could do that also with other figures, ray, line segment, or plane. And when we do that, when we cut a segment in half with one of these other figures, we call it a segment bisector. Okay? So when we know, when we're given a certain set of information, we can automatically determine some other things. In other words, on the left side here, if M is a midpoint on this segment, right, then what we know, and AB is kind of floating up here, but anyway, if M is the midpoint of AB, then what we will automatically know is that the segment AM is going to be congruent to segment MB. So here and here. We will automatically know that those two segments are congruent. So those two figures would be the same. Now, again, geometry existing in two different worlds, one when we talk about the diagram and one when we talk about numerical measures. If we know that those two segments are congruent, then we should also understand that the two lengths of those segments are going to be equal. Difference between an equality statement, which is here, versus a congruence statement, which is here. Okay? So again, the idea is we're given some information and we can automatically determine other information. That's what we're going to do in two-column proofs. When we start doing proofs, that's what proof writing is all about. Here's what I know. Here's what I can figure out because of what I know. Right? All right, so the same thing with a segment bisector. In the other box, line CD is a segment bisector for segment AB. If we know that, then we also automatically know that segment AM, segment MB are congruent, and therefore the length of AM is equal to the length of MB. Remember, and that yellow box reminds us up there, these tick marks tell us that segments are congruent. We'd want to use the same number of tick marks on two segments that are supposed to be congruent. Okay? All right. Using this idea of a midpoint, a couple of different ways we can do that. One example here, the emblem on the rear of a car is supposed to be placed at the exact midpoint of a segment connecting the headlights, or would be the tail lights probably, right? So anyway, the diagram shows it here. The emblem on the back of a car is going to sit right in the middle of that space, and we can draw a segment along the trim there connecting the tail lights. And that emblem is going to be right in the middle. So if that's the case, we have this segment XY that represents the distance between the two tail lights. And the emblem sits at T. So since T is sitting right at the midpoint, and since T is the midpoint, we automatically know that XT and TY are going to be congruent, those two segments. Okay? Now, what we also know is from the segment addition postulate that we should be able to add the length of XT to the length of TY, and that should equal the entire length XY, right? And that's what we have written here, the segment addition postulate. Well, if we know that XT is 39.9 inches, right, then we can plug that in for XT. But because T is the midpoint, XT and TY are going to have the same measure. So if we want to know the total distance between the tail lights, we can take 39.9 for xt, 39.9 for ty, and just add them together, so 79.8 inches. And that's because those two sides should be the same length. Okay? So an example here where we're using the midpoint, the idea of a midpoint, but we're still adding segments together to equal a bigger segment. But because we know that a midpoint creates two congruent segments, it does open up the possibility of not having to add those two smaller segments together. And then, for example, this next example here, point M is the midpoint of segment VW. We need to get to a point where we can draw this without a diagram, right? So if this diagram wasn't here, we'd still want to be able to draw segment VW and then plot M in the middle. And we would want to include, the second we put M in here as a midpoint, we would want to include tick marks to show that those two sides, those two segments are congruent. Okay? But the diagram's already here. So we know that VM and VMW are going to have the same measure. Those two segments are congruent. And we want to find the length of VM. Well, in order to find the length of VM, we got to know what x is, right? So we'd want to come up with an equation that we can solve using the information that we've been given. Well, since VM and MW are supposed to be the same length, we can take these two expressions and set them equal to each other. Subtract 3x, add 1, x is 4. So now that we know x, we can go plug in 4 for x and figure out what VM is, which is going to be 15. Now, since VM is 15, that means MW is going to be 15, which means that VW would be 30, right? So we can even find more information if we really needed to, just by knowing that M is the midpoint. Pretty powerful stuff. All right? So that's what a midpoint is and how we use it. We also want to be able to locate the midpoint, right? We talked before about points being used as a way to show location. We want to be able to do that for midpoints as well, right? So we do this all the time, at least your maps, Google Maps, Apple Maps, whatever, the basis behind those guys giving us directions is that is this, where we're using points to show location and then finding different measures between those, right? So what we would do if we wanted to find the midpoint between 2 points, right? Let's say we got 2 cities, one at A, one at B, and we want to find the exact city that's in the middle, right? We would put those points in a coordinate plane. We used to do that all the time in the form of atlases and maps, paper maps. We'd put those into a grid and then just use some geometry to help us come up with the middle city, right? The city that's right in the middle. Well, to do that, we put those points in the coordinate plane, we connect them with a segment, and now we want to find the point right in the middle, right? Since we're looking for the point that's right in the middle, right, somewhere in here, then hopefully it makes enough sense that we would find a point whose coordinates are right in the middle of the x coordinates between these 2 points and the y coordinates between these 2 points. So we're looking for a number that's right in the middle of the x's. So 2 numbers, -8 and 3. How do you find the number right in the middle of those 2 guys? Well, that by definition is your average, right? So in other words, we want to average the x's and average the y's, and that gets us to our midpoint formula right here. To find the midpoint of a segment, we would take the coordinates of the endpoints and then just average the x's and then average the y's, making sure that we keep those 2 numbers separate. These are coordinates to a point, and a point needs to have an x coordinate and a y coordinate. So we're going to list them as a point in parentheses with a comma to make sure that we understand that this is an actual point. So to get that done here, we would average -8 and 3. So that's done right here for you. -8 plus 3 is -5. Divide that by 2, and you get -5 halves. You could divide it out and get a decimal if you wanted to, or just leave it as a fraction. It makes enough sense too. And then average the y's, this 5 and this -6. 5 plus -6 is -1. And -1 divided by 2. Okay? And so there are your coordinates. -5/2, common -1/2 is the coordinate for this midpoint. Okay? So just average the x's, average the y's. Same thing here for this example, right? You saw the previous example. Go ahead and try to find the midpoint here. You can stop the video, start it back up, and see if you've done it correctly. There you go. Just add the x's up. 0 plus 3 divided by 2 gives you 3/2. Add the y's up. -5 plus -6 is -11. Divided by 2 is -11/2. And that's it. Those are your coordinates for your midpoint. Okay? Now, we can use the idea of the midpoint to help us find the other endpoint to a segment, right? So maybe we know we've got 2 points here, and I want to find a city that's on the other side of M here that happens to be the same distance away from the first endpoint D, the first city at D, right? So again, we put these locations in the coordinate plane, give them coordinates, and then go try to find it. Now, we can use algebra still. We can use the idea that to find the midpoint coordinates, we had to add the x's and divide by 2. To find the y coordinate, you had to add the y's and divide by 2. So doing this apparently got us this number, this 1. So x plus x divided by 2 apparently equals 1. Same thing for here, where apparently adding the y's and dividing by 2 got us 2, because that's the y coordinate for the midpoint. So we're just going to solve these. Now, we can plug the coordinates for D in here. So 3 for x and -2 for y, and just use some algebra skills. Multiply both sides by 2 here. Same thing here, because we're trying to get those variables equal, get those variables alone. And so we get 2, subtract 3, x is -1. Here we get -2 plus y equals 4, subtract, add 2, and y is 6. And so our coordinates for B are -1, 6. You can do it that way, but there's also a shortcut, right? I'll try to explain it really quick, and if you get it, use it. If not, then just use this algebra, and hopefully this will help. But if you look at the point D, right, since the midpoint is in the middle, we could take a look at how the x coordinates differ from point D to the midpoint. From the x in D to the x in the midpoint, we had to drop 2, right? We had to go from 3 down to 1. So we dropped 2, basically, right? That means to go to the other endpoint, you'd want to drop 2 again. Well, if you drop 2 from 1, you get -1. Same thing, we can do the same thing for the y's. From -2 to 2, we had to increase by 4. Well, just increase the 2 by 4, and you get -1, 6, just like we did when we used the algebra. So a bit of a shortcut. If that makes sense to you, then you can use it. Okay? All right. That's your midpoint. The next thing we want to do, since we're putting these segments in a coordinate plane, then we also want to be able to find the length of a segment. Before, we took a ruler, we measured the segment to find out what the measure was, right? But as you guys saw before, there were some issues there. One, we're using a man-made object in a ruler to help measure, so there's some error in the ruler itself because we're fallible, right? Man makes mistakes. Anyway, also, if the points are drawn big enough, there's some discrepancy on exactly when you start to measure. Where on that dot do you start to measure? So what we need to do, what we can do is develop some algebra to become a lot more accurate. Okay? And so we get to the distance formula is what we're going to use, because the distance between 2 points is the same thing as the length of a segment, right? So the distance formula finds distance between 2 points, but also finds length of a segment. Okay. How exactly? Well, quickly I'll show this to you. If I want to get from this endpoint to this endpoint, then I can't just walk straight to it. In a grid, it's like walking downtown Indianapolis, where you have to walk down a street and then over so many, down some streets and over so many streets. You have to walk in a grid, right? So from this point, this first point, I'd have to walk down, and I have to walk to the right in order to get to that other building, right? Well, same idea here. When we do that, when we draw those two paths in, we get a right triangle. And hopefully you remember, I know it's the first time you've not seen it, that we're trying to find the distance here, or the lengths, and then that'll help us find the distance here, or the length. So we're talking about the lengths of the sides of a right triangle. Well, the Pythagorean theorem is that relationship of the length of the sides of a right triangle. Pythagorean theorem says that the hypotenuse squared is equal to the legs squared and then added together. Okay? All right. Well, if we get in here and use these generic coordinates for the endpoints, we can come up with a generic set of coordinates for that point. This point at the right angle is the same distance over to the right as this point is. So this coordinate would be x1. It's also the same distance up as this point is. So the y-coordinate would be the same as that point, which is y2, x1 and y2. Well, if I want to find this length, the ruler postulate says that we can use the coordinates and subtract them. Well, since going up and down is moving in the y direction, then we would use these two guys and make the length of this segment y2 minus y1. And since this direction is in the x direction, we would make this side x2 minus x1. Those are the legs of our right triangle. And so these guys go in for A and for B. Right? And so that, when we plug that in, it would look like this. Right? So that's why we have this x1 minus x2 squared plus y1 minus y2 squared. Okay? Now, from the Pythagorean theorem, that gives us the length of this side, which is the hypotenuse, but not just the length. It gives us the length squared. It gives us that distance squared. So what we do now is, to get the actual just the distance, we want to square root both sides, and that gets us to this formula right now, right here. So hopefully that made enough sense as far as where this formula comes from. If not, that's the formula. Just be able to use it. All we're going to do is take the two coordinates here and plug them in for the x's and the y's down here. All right? And then do some arithmetic. Let's take a look and see how this works, right? So here's a segment, RS. It has those endpoints. The endpoints have those coordinates. And we want to find the length of that segment, right? We want to use the distance formula. X1 or whatever, x1 minus x2 or x2 minus x1. What we need to talk about here in a second is it doesn't really matter which way you write this. Okay? All right, so basically subtract the x's. The x's here are 4 and 2, so subtract those and then square it. The y's are 3 and negative 3, so make sure that you're subtracting the negative 3. So you got 3 minus a negative 3. That matters because now this is going to turn into 3 plus 3. So this is 2 squared plus 6 squared. 2 squared is 4, 6 squared is 36. So we get the square root of 40. And so if we want the approximate length, then we can go ahead and square root this. I think get about 6.3. Okay? If we wanted the exact length, we'd leave it in radical form and reduce it, but here we type it in and get an actual decimal answer. Okay? So that's how we use the formula. Just plug in the x's, plug in the y's, and then do your arithmetic. Okay? All right, you try it on this one. Be very careful with how you square numbers, but give it a shot. Stop the video, start the video back up when you're done, and make sure that you've done this correctly. And you should have gotten the square root of 109, which when you type that in, sorry I didn't do that, so let me do that really quick. You should get 10.44. Okay? And that leads us to the last question. Does it matter which ordered pair you choose to use first in the distance formula, y or y not? Right? In other words, does the order of the x's and the order of the y really matter? Right? Well, think about this, and we'll take a look at just one part here, right? We'll pull this out to the side. Inside this radical, we had negative 3 minus 0 squared, which was negative 3 squared, which should be positive 9, not negative 9. I don't care what your calculator says, right? Now, what if we flipped it around? What if we made it 0 minus a negative 3? Would that really change anything? Well, that would become a plus, and this would become positive 3 squared, which happens to also be 9. So you get the same result. So apparently the order in which you subtract the x's or the order in which you subtract the y's doesn't matter. And why does it not matter? Because we're squaring these. Because we're squaring those the difference in that formula. And anytime you square, whether it's a negative number or a positive number, you're going to get the same result. It's going to be a positive whatever, right? So that's why it doesn't matter the order in which you subtract them, which is kind of nice. Okay? Just watch those negatives. Negative numbers squared are still positive. Okay? All right, that's it. Distance and midpoint formula there and the idea of a midpoint. So homework's out in Canvas. Make sure you have that done by next time.